This video covers Griffiths E&M section 5.3 divergence and curl of the magnetic field. Let's think about a simple scenario where we have a wire that carries a current I down, let's call it to the right. Okay. If I were to calculate what that magnetic field was, which is something that we have done previously, I would find that that magnetic field is mu naught I over 2 pi s in the phi hat direction, meaning that above the magnetic field, or above the wire, the magnetic field is pointing out of the page, and underneath it is pointing into the page. Right, and that strength decreases like 1 over s, which s is the distance away from the wire. If I were to go ahead and turn for a side view of this and look at the wire carrying an I into the page, I would then see a magnetic field that is looping around like this. Therefore, unlike the electric field, the curl of that magnetic field is not equal to 0. All right, so let's figure out exactly what that curl of that magnetic field is. And I'm going to first do that by drawing a loop. I'm going to go ahead and draw this loop right where I drew these field lines. And I'm going to traverse that loop in this direction. And I'm going to take the integral around that whole loop of my magnetic field dotted with dl. Okay, I know that dl is going to be pointed in the phi hat direction, just like my magnetic field is, because that's the way I chose to draw that loop. So I have this dot product between mu naught I over 2 pi 1 over s in the phi hat with s d phi in the phi hat. Those are the same directions. The dot product gives me 1, and I'm left doing this whole integral mu naught I over 2 pi, the s's cancel, over d phi, and that d phi goes for the whole loop 0 to 2 pi. All right, there's no phi in here, so the integral just gives me a phi, and therefore that integral is just mu naught I. All right, so I have this expression that the contour, or that the closed path integral along my magnetic field gives me mu naught I. Okay, so what if I were to have a different case where maybe I had multiple wires all carrying a current I, and I wanted to know what the magnetic field was there. All right, well, I can still draw a loop. I'm not going to shift this frame, but I'm going to go ahead and draw this loop where I am going to go all the way around. I'll go this direction. The reason for this example is that now I'm going to go ahead and say that this dot product is not just the current of a single wire, but is now all of the current that is enclosed by that loop. Right. All of the current that pierces through that loop right there. Okay. But I know the total current is just whatever that current density is dotted with the area. In this case, I'm defining that area as the area that connects that loop in a simple plane. Okay. So I can go ahead and rewrite, using Stokes' theorem, this part of that expression. That is going to be a new dimension. Instead of b dot dl, it is going to be the curl dotted with dA. All right, and then that expression I'm just going to bring down here. Now I'm still mu naught j dot dA. Well, if that's true for, if this is an integral over the surface, and I'm doing the same integral over the same surface, then that's true for all surfaces. So I'm left with the meat of those integrals. The curl of B is now equal to mu naught J. This is Ampere's law. All right. We have Ampere's law. Remember Gauss's law? Gauss's law says E dot dA is equal to mu naught Q enclosed. And basically, you have a bunch of charges. You draw some Gaussian sphere, some surface, and you count the total number of charges inside. And if that total number nets to something that's not zero, then you have an electric field at that surface. Let's make the same analogy, but in magnetostatics instead of electrostatics. I'm going to go ahead and say, all right, here's my sphere. Here's my magnet. I have a north end and a south end of my magnet. How much total stuff is inside of that sphere, that Gaussian sphere? Well, if we're saying that north and south are kind of like opposite charges of magnetic particles, then they're going to cancel out. Okay, I'm always going to have no net source of magnetic field inside of this loop or inside of this sphere. Okay, well, you might say, well, perhaps you can just cut it, right? Well, if I cut that in half, now I'm gathering a new north and a new south, and therefore the net number of north/south poles that I have is still zero. Okay? So until a magnetic monopole exists, which it probably doesn't, we're always going to be able to say that integrating over this whole surface, all of the magnetic field that leaves is just zero. Yeah, so that's a hand wavy thing, but there's another proof in equation 550. Okay, so I don't know if this expression has a name, but we talked about Ampere's law. We have this this other B dot dA is equal to zero, and now we have officially seen all of the Maxwell's equations in some form in this class. Okay, we have Gauss's law. I'll write these all in differential form, all of the Maxwell's equations. All right, that is 1 over epsilon naught times charge density. The curl of that electric field is equal to 0. The dot product of my magnetic field is equal to 0. And the curl of my magnetic field is equal to mu naught J. These are all the Maxwell's equations in terms of the electro and magnetostatics. Okay. So if you could calculate the electric fields from the charges and the magnetic fields from the currents, you can then calculate the force that a just charge feels in the presence of an electric and magnetic field. And that's the whole goal of this class.